As promised, more on the Cambell causal model. Between this video and the last, I've checked in on the relevant sections in the knowledge base. Glad that I did. Not sure I'm on the same page, so I'm going to sort of give you a fair warning here that sort of the assigned reading material, these conflicts between the assigned reading material and my interpretations of things should be resolved in favor of me. More on that in a minute. Back to Cambell. So this language, internal and external validity, I'm going to relate it back to measurement validity, something we've already covered. You should already know. A measure is valid to the extent that it taps the concept that it's intended to measure. Cambell builds measurement validity into his grand critique, actually a career-long critique, of the validity of causal inferences. He builds it in under the name of something called construct validity. It's the same thing. And we would start there. Measurement validity, and remember measurement reliability, they relate to these two things, but this is more than about measurement. It's about the inference of cause and effect more generally. You think about it as the validity of a study or of a study's results in two different dimensions. One internal to the study itself and its design, and one external to the study relative to other potentially applicable units. I'm talking in the external validity about the generalizability of results. A study is externally valid to the extent that its conclusions can be applied not just to the subjects who are part of the research, but across all people, across all time, across space, anywhere, across place. A study done in Wisconsin is externally valid if it's also applicable to people similarly situated in Alabama or California. So external validity is all about generalizability, and internal validity, in contrast, is about the intrinsic sort of control afforded to the researcher. This is where I'm sort of departing from the knowledge base descriptions here, sort of maybe some implication there that the term observational studies over here, I just have an xi in one direction, so x causes y. My definition of observational study is any study that's not a true experiment. Any study that's not a true experiment is, in my world, an observational study. And the true experiment, one more time for emphasis, you can bet this will be on a test. The true experiment has this is TR for treatment group, and CON, short for control group, has the treatment and control group determined, whose membership determined at random. So any study that does not have random assignment from treatment to control group, and there are plenty that don't, is somehow quasi experimental, if there is any attempt at causal inference at all. And those I call observational. And I'm going to get to the end and talk about kind of the most observational sort of study that we do. First, okay, external validity is about making inferences across time, space, people. It's about generalizing results, and internal validity is simply about this. Those three, the three rules that were up here in the last video, revisit those. A study is internally valid to the extent that it does those three things, that establishes that X and Y are related, that it establishes that X comes before Y, or that Y didn't cause X. And third, and most difficult, that it controls for all potential confounding influences that could make it appear as though X and Y are related, when in fact there's no causal relationship at all. That last sort of situation is what people refer to when they say correlation is not causation. Things can be related and yet one not cause the other. Should I sort of examine or say something to finish out Cambell about experimental designs and observational designs in the context of their occasional or typical strength in terms of internal validity or external validity. So on internal validity, the experimental design gets a huge plus here for random assignment. If I keep explaining something, it's because it's critical. Those things, those attributes of individual units of analysis that could confound our understanding that something caused this, instead sort of make us believe that something was just correlated. Anything, it can, in theory, be controlled by random assignment. So this is the key. Now, a potential problem for the internal validity of studies relates to sort of a norm, I guess, in experiments, or we think of it as a norm, and it's kind of a past norm. I'm reading the knowledge base and I'm seeing sort of a generalized reference to small and unusual samples being involved in true experimental designs, and sort of the reference there suggesting that they're rare. That's dated. Experiments are increasingly common in political science and other social sciences, and they do risk, there can be risk to the internal validity of the study because of the size of the sample. So if we have 20 people and we assign 10 to the control group and randomly, and 10 to the treatment group, yes, there can be enormously faulty inferences that are just brought about by chance. It's kind of a chicken or the egg thing presentation-wise on inference. I'm doing causal first, statistical second. If we'd done statistical first, this would make more sense, and I would be able to formalize it more. You've got it on tape, though, so you can come back here after you've seen the statistical inference stuff and probably recognize that if you had 20 people in the study divided into two groups at random, it's going to put you at risk of making a faulty inference and that's really due to something outside of your control. Large N, a real large sample of people randomly divided into two groups, treatment and control, administer the X to one and not to the other. That's the gold standard for internal validity and the gold standard for causal inference, really more generally. External validity and experiments, it's a positive if you have a representative group, and if you have a large group, chances are better that it will be representative, because we'll see subsequent to the statistical inference presentations that representativeness really relies on two things: the size of the sample and the way that you go about selecting the sample. But just generically for now, just think of you want a representative group, because if you've got an odd group, chances are that you could find an inference that would not be generalizable to external audiences. A good example is young people. Psychologists, forgive them, and now political scientists too, increasingly give extra credit to students to participate in an experiment. And it's a gigantic tome of knowledge built up over the decades that really derives directly from experiments conducted only on people between the ages of 18 and 21. Not a representative group. Now, many times they're talking about cognitive, psychologists are talking about cognitive processes that should really be kind of consistent across age groups, and so there might not be a problem. Attitudinal studies, on the other hand, are probably particularly at risk here. Think of a test of whether some presentation, maybe by a professor, but a presentation of anything, to a control and treatment groups consisting only of 18 to 21. Let's limit it to 18-year-olds, freshmen, entering freshmen. They're our experimental group. We randomly divide them into treatment and control groups, hoping to reach the gold standard. We find an effect where we can invoke an attitude change, measured Y. We deliver some X, say a video or a presentation. Then measure again time t plus 1, and we find a change brought about, and someone might make an inference from that finding to not just 18-year-olds, but everybody else, would be risky. Because as it turns out, if you're between the age of 18 and 21, you're developing, especially in political science, you're developing right now the first attitudes of your own, and you're more likely to change than your parents. And you can actually think about that and understand how likely is it that you might change from being a Republican to an independent, or a Democrat to an independent, right now. And also think of your grandparents. How likely is it that they will change? It's more likely that you will, and thus findings on sort of unrepresentative groups would be a negative. Findings on unrepresentative groups are very risky to try to generalize. If you did some study in political science, experimental study on attitude change only on college freshmen, it would never likely make it into a top journal because of that kind of criticism. What's the other we've got? Observational studies. Lower on internal validity. Wow, that helped. Lower on internal validity because of no random assignment, and often with observational studies it's easier to grab more data. Implementing experiments is difficult and requires all sorts of things that observational studies don't. And so it's sometimes easier to get a large N, and that's that can help even in the internal validity dimension, because it gives you more. We'll learn about these degrees of freedom, things to do. It's a plus if your observational design has some experimental-like qualities, so-called quasi experimental. You could have a pre-test, a treatment, and a post-test. For example, in a grade school, you're going to try something new with first graders, and so you test them beforehand, and you try the new thing, the new teaching method or whatever, and then you test them afterward. That begins to look like the top line here. What you left out was the control group. It's good to have a pre-test and a post-test. There are risks with it, and that's covered extensively in the materials that you've been assigned, so I won't really go there. But just say this: to the extent that you can make your non-experiment have qualities that are characteristic of a real experiment, a true experiment, it's better on internal validity. See, this term, probability sample, again is something for statistical inference, which comes after the current set of videos. But it's used to be easier to get a probability sample to do observational studies and correlational studies, and it's very representative and can be sort of on the generalizability dimension. This is a real positive if you can do that. Non-probability samples typically are really, really, really bad for external validity and being able to generalize. Now, there's a school of thought, transitioning quickly. Last thing, school of thought in political methodology these days, this has become sort of falling out of favor, making causal inferences from observational data, from data where there were no random control trials. There's no real control of the circumstance by the researcher, and yet, in defense of those, I'm going to reason with you through a model that's well established in the political science literature that no critic I know would take on very seriously. If you had me for 101, you've seen this before. This is the Michigan model of voter choice. So-called Michigan model. So you have down here partisan vote, sub-I. And we'll think to 2012. Just last year, this is a presidential election pitting Mitt Romney, the Republican, versus Barack Obama, the Democrat. The voter choice has been the object and the subject of just hundreds and hundreds of studies in political science across the decades, and beginning in the 1960s, there's a sort of an emergent view of what causes people to decide between a Democratic candidate on one hand, a Republican on the other. You can't really generalize. It's not easy to generalize this model outside partisan choice, but let's think of that. So you got partisan votes, so 0 equals Obama, and 1 equals Romney. And so remember that the I voter in our data set chose either Obama or Romney, and we're going to consider only voters here. So we're going to say why do they do it. This might prefer on the observational side, great preference on my part for really, really simple models. One reason is that this thing is so powerful that it really can't be replicated in quasi-experimental designs. So complex on the observational side, to me, typically is a downside of observational studies. You want to control for those things that are obvious and build sort of a causal explanation of why something happens. So I'm going to put a circle around that, and I'm going to limit my explanations to 3. And there's a very compelling, to me, paper from political methodology from not about a decade ago, maybe a little more, essentially saying that we should always limit our explanations to 3 in this kind of study, observational, without random control trials. So what causes partisan vote is the question, and one of them is party ID, PID. So many of you identify yourself in party conflict. Some of you say, I am a Republican. Some of you say, I am a Democrat. Others are, I'm an independent. I'm in the middle. We've already seen that's an ordinal variable, right? Ordinal level measure. It's a very strong predictor. It's a very, very proximate cause. I don't have experimental evidence to show you. It is, however, a very proximate, important cause of the decision of whether you will vote for Obama, who is the exemplar of the Democratic Party, or Romney, who once nominated, became the exemplar of the Republican Party. So this is a big, huge cause, right? And yet, Republicans can go off the reservation and support a Democrat, and Democrats can go off the reservation and support a Republican. Not often, but sometimes. And most importantly, independents are in the middle here, so we don't have everybody in this explanation. So we put issues as one. Believe it or not, partisanship really causes, and I guess you could say that too, that issues can cause partisanship. Much of the research today is dedicated to trying to understand the extent to which we take positions on issues because our parties lead us to. Nonetheless, you can disagree. So think back to maybe easier to talk about Barack Obama versus George Bush rather than Obama versus Romney. So President Obama today is Commander-in-Chief of the Armed Forces and has prosecuted wars in Iraq and Afghanistan. In 2008, when he ran against George Bush, I think people saw him as the candidate of no war, and Bush as the candidate of war. And so that's an issue, and it's one where many Republicans didn't agree with the way the Bush administration had handled the war. So you can be a Republican, disagree, and go the other way. So issues matter, and they vary from election to election. And what else? Candidate evaluations. I'm going to call this likability. Like, survive. Our partisanship helps determine who we like. Democrats liked Obama in 2012 better than Republicans liked Obama, and Republicans liked Romney in 2012 more so than they liked President Obama. And yet you can still can be a likability differences that work on independents, that can work on partisans who are leaning, maybe because of an issue. And you can use this model to interpret election after election after election, going back in history. And it's anecdotal to use it. And that's not scientific. And yet, I really challenge anyone to suggest this is not a reasonable, individual level model of partisan choice in presidential general elections. It comes to us not through experimental evidence, but through literally decades and decades and decades of survey evidence and observational statistical evidence that sort of, at this point in time, seems beyond almost any debate. This is doing science. What I just did, sort of, okay, partisanship's one explanation, issues another explanation, likability is a third. This is doing science on the observational side of things. And if you're going to add data, and in this class we're going to look at data about this very topic, add data and then you're doing science, it's kind of quasi-science because there's no random assignment, no control by the researcher. And doing science over here is more difficult. It's more difficult. It's easier with the computer and the sort of ubiquity of the connections people have today via the web, but it's really hands-on control by the researcher here to make sure that one group goes randomly into the treatment group and one group goes randomly into the control group. That, I think, is it for Cambell, and then onward.